Hello everyone, welcome to join our tutorial. I'm Jahan Lu, a professor at the Department of Computer Science, University of Helsinki, Finland. This tutorial will be given by Chao Zhang and me. We come from a research group at the Department of Computer Science, University of Helsinki. The main research topic of our group focuses on database theory and algorithm. Especially on multimodal database, we develop a benchmark system for multimodal database called UniBench, which will be introduced in this tutorial. If you are interested in our research, please access our webpage for the details. In this tutorial, we will first give an introduction to big data system benchmarking. Then we will introduce 4 types of the benchmarking system, including the SQL benchmarking systems, MapReduce, NoSQL systems, graph database benchmarking systems, and the multimodal database benchmarking system. Finally, we will discuss the open challenge and the future direction. We are in the area of the big data. Big data is a field that deals with data sets that are too large or complex to be dealt with traditional data processing application software. Data come from the varied sources, include the web, e-commerce, bank systems, social network, scientific data. Data sets grow rapidly because they are increasing gathered by the cheap and the numerous Internet of Things devices, such as mobile devices, software log, cameras. Big data challenge, including capture the data, data storage, data analysis, search, sharing, visualization, query, and update big data. The traditional databases are not capable of handling high-volume datasets. It is a challenge to store, manage, process, analyze, visualize, and extract the useful insights from the big data. Different systems are developed to address this challenge to handle the big data. Those systems are called big data systems. Typical big data systems include Hadoop, Spark, and Hive. In this tutorial, we will focus on different big data benchmarking systems, which are a suite of programs that make competing products comparable and help users to choose the right big data systems. Those benchmarking systems can help users to identify the performance bottleneck to make big data system better. Because one size does not fit all, we need different benchmarks for various systems and scenarios. The key elements of our benchmarking systems, including the data domain and data schema, synthetic data generators, specified workloads such as queries, performance metrics such as latency, and specific execution rules to run those benchmarking systems. We classify the existing benchmarking systems into 6 categories, including MapReduce-based, NoSQL-based, SQL-based, graph-based, multimodal-based, and others. For each category, we find the representative systems, examples, and benchmarking systems. In particular, for MapReduce-based systems, Hadoop, Spark, Flink are representative systems And the benchmarking systems, including AMP, Big Data Benchmarks, and HighBench. For NoSQL database, the system includes MongoDB and Cassandra and Radius, and the benchmarking systems include the YCSB. For SQL-based systems, the system includes Hive, Teradata, Presto, Spark SQL, and the benchmarking systems include TBCH, TBCDS, and Big Bench. For the graph-based systems, the systems example include Neuro4j, Janus Graph, JGraph, and the benchmarking system include the LDBC, Graph Analytics, SMB. For the multimodal database-based systems, the system include ArangoDB, OpenDB, NGSGraph, and the benchmarking systems include the TBCDI, Polybench, Unibench. And for the other system, including streaming, spatial, RDF, and the macro benchmarks. In this tutorial, we will discuss these 5 types of benchmarking systems and introduce their data generator, workloads, and performance metrics. You are expected to acquire the following knowledge after this tutorial. First, you will understand the key technique of various big data benchmarks. Second, you will learn the relationship of the big data benchmarks and their applications. Finally, you will understand the current practice and future direction for big data benchmarking. The total length of the tutorial is about 2 hours. Okay, now I will pass the floor to Chao, and he will first introduce the benchmark for the SQL big data analytical systems.
Hello, everyone. I'm Chao Zhang from University of Helsinki. In the next, I will talk about the SQL-based big data analytical systems. So the Transaction Performance Console, or TPC console, is the most professional organization in benchmarking SQL analytical systems. It aims at complex business analysis applications with structured data. And it has developed a number of standard benchmarks. In this tutorial, we look at 3 representatives: TBCH, TBCDS, and the TBCBB. So the TBCH is a very popular benchmark in the field of data systems, as shown in the figure. TBCH was referenced in more publications than its successor TBCDS and TBCHS in the past 10 years. So it's based on a business analysis application with 8 tables, and it provides a data generator with the factors for scalable data generation. For the workload, it contains 22 business queries with choke point designs. So the choke point design is also known as benchmarking challenges, which database systems have to solve in order to achieve good benchmarking results. So in total, TBCH queries contains 28 choke points, and Peter Bones et al. At TBC TC 2013 have classified them into 6 categories: aggregation, join, data access locality, expression calculation, correlated subqueries, and parallelism and concurrency. And one query may involve multiple choke points. So let's take a query 7 as an example. So the query 7 is about volume shipping. And this is a join query that joins 6 tables, including customer, nations, order, line items, and supplier, etc. So therefore, finding a efficient join order is important. So the first choke point, 2.3, is join ordering, which is aimed to select optimal join order. In addition, the second choke point is the 4.2b, which is about the join dependent expression filter push down. So this means the TPCH will rewards optimizer that can analyze complex join condition that cannot be pushed down the join. So for instance, if the plan would start by joining the customer to the nation, so it could immediately filter the condition for N2 in the join conditions. And the TPCH defines several metrics. The main metric is the composite query per hour performance metric, which includes 2 parts: the power test performance and the throughput performance. So the power test performance means the queries are executed in a sequence with 2 fresh functions, and the throughput metric test is executed in multiple streams, where each stream consists of a power test. It also considers other metrics. For example, the price performance matrix, which is computed by the price divided by the performance matrix, and also the availability date, which can be defined as the 59% per year, and also the energy matrix. However, despite the popularity, TPCH has several limitations, such as linear scaling of tables, homogeneous data distribution, and it used the third norm form rather than the star schema. And the workload only involve the simple structure ad hoc queries, and the update workloads are simple. So the TPC developed a benchmark TPC DS for replacing the TPCH for decision support benchmark, and it introduced the TPC DS version 1 during 2000 to 2012, and then it introduced the version 2 in 2015 to support Hive, Hadoop, and other features. So it has a snowflake schema with 24 tables, including 7 fact tables and 17 dimension tables. And it has a more realistic data scaling with non-uniform distribution. And for the workload, it identifies 99 query templates with 4 types: reporting, ad hoc, iterative, and data mining queries. So for the reporting query, and this query will capture the reporting nature of DSS system, and they include queries that are executed periodically to predefine question about the financial and operational health of a business. So for example, the query 3 is to report the total extended sales price per item brand of a specific manufacturer for all sales in a specific month of the year. And the second category is the ad hoc queries. So the ad hoc queries capture also the dynamic nature of a DSS system in which input queries are to answer the immediate and the specific business question. For example, the query 42 asks for each item and the specific year and month to calculate the sum of the extended sales price of stone transactions. And the third category is the iterative OLAP query. And this query allows for exploration and analysis of business data to discover a new and meaningful relationship and trends. For example, the query 22 asks for each product name, brand, class, category to calculate the average quantity on hand and will load up data by product name, brand, class, and category in multiple iterations. And the final category is data mining queries. So this query will analyze the data to predict the future trends and behaviors. For example, the query 82 to find customers who tend to spend more money online than in stores. So for the execution rules, it consists of 6 phases: system setup, database setup, database load, query run 1, and the data maintenance and the query run 2. And the first 2 phases are on time, and only the later 4 phases are timed. So for the database load phase, the TLD will measure the loading time, and for the query run 1, it will measure the power test performance plus the transaction performance. And the third phase will be the performance for the data maintenance. So the TBCDS is modeled the data maintenance process as an integral part of the whole process, and this process will be modeled as the ETL process for data extraction, data transformation, and data loading. And the final phase is about the query run 2, where measures the throughput phase 2. So finally, the main metric is the query per hour performance metric. So generally, the higher the skew factor, the higher the number of query stream that must be processed. And then Q is the total number of weighted queries. And finally, the QPHDS will be computed as a square root of the 4 phases. So at 2016, TBC proposed the TBC-BB, which is an end-to-end application level benchmark for big data analytic systems. So it's based on TBCDS and originated from the proposal Big Bench version 1 at SIGMOD 2013. And this benchmark features the variety, volume, and the velocity of big data. So for the variety of TBC-BB, it has a data model including structured, semi-structured, and unstructured data. So this figure shows the data model of TBC-BB. And the structured component of Big Bench or TBC-BB is adapted from the TBCDS benchmark. And they also introduced a new table named market price for competitors' name and price of each items. And the semi-structured data focus on the claim streams contained in the web log, while some of the streams will result in online sales. And the unstructured data contains product reviews of items by the customer. So the customer can be registered users or guest users. For the volume of TBC-BB, and so the size of structured data uses the same scale factor to TBC-DS. And for the item of market price, it is assumed that an average of 5 competitors' prices are stored for each items. And the size of web log depends on the number of clicks made by the buyer and the visitors. So the buyer clicks depend on the web sales, page per item, page per buyer, and item per sale. And for the visitors clicks, it's based on the web sales, page per item, and the visitor ratio. And it assumes that the 80% of surfers are visitors. And for the reviews, a similar approach is chosen. That means these sources of reviews are based on the anonymous reviews, random item reviews by registered customer, and the reviews based on sales. The data generation is based on a parallel data generation framework, short for PDGF, and it's implemented in Java and fully platform independent. It's a scalable and extensible data generator with 2 XML documents for configuration. So including the schema configuration and the data generation configuration. And it has a random seeding strategy, which assigns seeds to the tables, the columns, and the rows of a database schema, and thus make it possible to generate data in parallel. In addition to the PDGF, the TBC-BB also developed a separate review generation process for the unstructured data generation. Concerning velocity, TBC-BB simulates a periodic data refresh process considering the amount of data and the time interval. So the number of refresh process executed in a linear function of the number of query stream S. So it defines different data refresh velocity for structured, unstructured, and semi-structured data, particular 1 for structured data, and 2 for unstructured data, and 4 for semi-structured data. And for the refresh process, it requires that at least 3 times S queries must complete before the first refresh set can start, and at least the Q date type minus 6 additional queries must complete before the second refresh set can start. So by this definition, the fresh velocity will be defined. And overall, TBC-BB workload consists of 30 complex queries, and 10 of which are based on the TBC-DS. And it identified 5 business categories from the magazine reports, including the marketing, merchandising, operations, supply chain, and the new business models. It also considers 3 technique dimensions, including data source, processing type, and analytic technique. And the matrix is mainly similar to the TBC-DS, including the loading time, the power test performance, the throughput performance. with the skill factor, and where the M is the number of query in the benchmark, and the SF is the skill factor, and the factor of 60 in minutes in an hour. So the TPC-BB defines the queries in English text. So in the next, we take an example for each category. So for the marketing, the query 1, we compute the probability of browsing products from a category after customers view items for another category. And for the merchandising, the query 6 measuring the impact of price changes on sales for price optimization. And for the operations category, the query 8 will first find products with high return rate and then identify if there are any issues from product reviews. For the supply chain, query 9 computes the mean and the variation of item inventories and identify those with large variation. And finally, for the new business model, the query 10 measures the effect of competitors' price on products in store and online sales for price comparison. So the TPC-BB queries are implemented by Hive query with MapReduce, NLP, and the machine learning programs. So take the query 10 as an example. It asks for all products, extract sentences from its product reviews that contain positive or negative sentiment, and display for each item the sentiment polarity of the extracted sentence, pause or neg, and the sentences and word in sentence leading to this classification. So this query implemented by Hive query with NLP programs, and also based on the MapReduce framework. So this query retrieved from the reducer function called extract sentiment that takes input the source table product reviews, and this calls the function also specify the column that has the test and the model for the sentiment analysis, and the search label as a sentence, and the where clause at the end picks positive or negative polarity. So the TP vendors can release their results in TPC. So for the TPC-BB, the recent top 8 results are shown here. So the Alibaba Cloud, Max Compute system tops the list with BBQ PM 26,000. And since the TPC believe the comparison of TPC-BB results measure different datasets are misleading and discourage such comparisons. So here the comparable results is also released by Alibaba at 2019 with the same skill factor. So we can see their recent results have higher BBQPM and lower price and less nodes. In the following, we will talk about the benchmarking MapReduce NoSQL systems. So the MapReduce paradigm is proposed by Google at OSDI conference at 2004. It has been widely adopted since Yahoo released its open source version Hadoop at 2009. Although Google has no longer used it as a primary model since 2014, the concept of MapReduce is still critical to many applications. So basically, a MapReduce framework is usually composed of three steps: the mapper, and the shuffler, and the reducer. So for the mapper, each worker node applies a map function to the local data and writes the output to a temporary storage. And in the shuffle phase, workloads redistribute data based on the output keys, and such that all data belonging to one key is located on the same worker node. And the reducer will finally process each group of output data. So the representative open source systems are Hadoop, Tez, Hive, and Spark. And we will look at two benchmarks, AMP Big Data Benchmark and HiveBench. And we will also discuss the main finding from their existing evaluation. So the AMP Big Data Benchmark is developed by Berkeley, and it's originate from the paper A Comparison of Approach to Large-Scale Data Analysis by Andrew Pavlov et al. Sigmund 2009. And it uses three simple datasets. The first one is the unstructured HTML documents. And the second one is ranking tables with the page rank value. And the third one is the web log for the user visits for over the websites. And this benchmark defines 4 queries. So the first query is a simple selection query over the rankings table with a page rank value filter. And the second query is aggregation query over the user visits tables. And the third one is a join query between the user table and the ranking table. And finally, the fourth query is a UDF query, which calculates a simplified version of PageRank with a Python script. So the AMP benchmark have conducted an evaluation over 5 systems. The first one is the Amazon Redshift, which is based on the massively parallel processor architecture, and the Hive, based on Hadoop, and Shark, based on Spark, and the Impala, based on the MPP, and also the Tez, based on the Hadoop. And their main findings are as follows. So for query 1, the best performers are Impala and the Shark. And for query 2, the Redshift is best because of its column storage. And for query 3, Redshift is also best because of network capacity. And for query 4, Shark is a winner because of also the in-memory computing. However, the third insights may be doubtful, because in benchmarking we normally define the same experimental setup for all systems. So the network capacity should be the same in the setup. So the original evaluation is conducted by Andrew Pavlov et al. At Sigma 2009, and they benchmarked the system over a 100 node cluster with 3 tasks. They evaluated the Hadoop and a relational database, the DBMSX, and a column relational database, Vertica. And this table shows the results for 3 tasks: grip selection, web log aggregation, and join. So we can see, surprisingly, the DBMSX is 1.5 times better than the Hadoop, and 1.6 times better than Hadoop in weblog, and 36 times better than the join, and the Vertica can do even a better job than the DBMSX because of the column storage. So the Michael Stonebreaker from ACM Communication 2010 have gained insights from the following 4 aspects. So first of all, they believe the IMR processing model is slower because of the repetitive record parsing, and it writes the intermediate results into disk, and it's block-based scheduling, while the relational database can do the tuple-based scheduling without parsing the records, and without write the intermediate results frequently. And the second one is from the user level perspective. So compare with the easy to use setting up of Hadoop, parallel DBMS actually needs the one button install, automatic tuning, and better documentation. And the third, they believe the parallel DBMS excel at the efficient querying of large datasets, while the MR style system excel at complex analytics at ETL tasks. So this means these two types of system actually are targeted at different application. So the best solution is to combine the parallel DBMS with the IMR framework, and the representative are the Hadoop DB, Aster, Greenplum, Cloudera, and the Vertica. So in addition to the AMP Big Data Benchmark, the HiBench is another popular big data benchmark suite with 4 categories, including the micro benchmarks, the web search benchmark, the machine learning workload, and the HDFS benchmark. And recently, the HiBench 7.1 with also adds a streaming workload and a parallel graph algorithm. And at VODB 2015, the Ju Weishi from Renmin University and IBM conducted the evaluation over the MapReduce and the Spark, and they have 2 important insights. The first one is the Spark is about 2.5 times and 5 times faster than MapReduce for the word count, key means, and the PageRank workloads respectively. And the main causes of these speedups are the efficiency of the hash-based aggregation component for combine, as well as the reduced CPU and disk overheads due to the RDD caching in Spark. So in other words, the Spark can use the in-memory computing to speed up these workloads. However, they also found that the MapReduce is 2 times faster than Spark in sort workloads. So they found that MapReduce actually can overlap the shuffle stage with the map stage, which effectively hides the network overheads, while the Spark will use the DAG query execution when cannot overlap these phases. However, they used the Hadoop version 2.4 and the Spark 1.3, and now these systems have evolved a lot. So these insights should be validated further. And there are other big data benchmark solutions: the Yahoo Cloud Serving Benchmark, the Yahoo Streaming Benchmark, and the Big Data Bench. So the Yahoo Cloud Serving Benchmark, or YCSB, is aimed for the cloud-based OLTP systems, and the focus is on the throughput, scalability, and the elasticity of the system. And there are also extensions include YCSB++, YCSB plus T, etc. And the workloads include 4 types. And the second one is the Yahoo Streaming Benchmark, which simulates a simple advertisement application. So this benchmark talks at streaming systems such as Stone, Flink, and Spark Streaming. So the architecture is as follows. So first of all, the benchmark will read an event from Apache Kafka and deserialize the JSON stream, and then do the benchmark operation in the pipeline. First of all, we'll filter JSON, pass and the transformation JSON, and do a join between the platform and the radius, and then use a window aggregation, and finally do incremental computing and store the results into the radius. And recently it has been pointed out that the radius could be the bottleneck rather than the streaming processing. So this might be an issue for this streaming benchmark. So the final big data benchmark we'll be talking about is the Big Data Bench. So it's also a big data benchmark suite by Jianfeng Zhang from Chinese Academy of Science, and it belongs to the International Open Benchmark Council, Bench Council, and it is proposed from the 2013, and now by developing more benchmarks and more workloads, it evolved to the Big Data Bench 4.0, and this benchmark now includes 13 real-world datasets and 47 benchmark and 7 workload types. And also recently they have proposed the AI bench with 17 AI-based tasks involving the image, video, and text tasks. And in the next, we're going to talk about the graph-based big data systems. So there are two types of graph data systems: graph databases and graph processing systems. So the graph databases is focused on the OLTP and light OLAP operations. Representative are Neo4j, Genius Graph, and Blaze Graph, etc. And the graph processing systems focus on the heavy OLAP operations for business intelligence and batch algorithm. So these representatives are GraphLab, Graph, and GraphX, etc. And they also share some overlaps on complex query, pathfinding, and connectivity. So in this field, the LDBC is a pioneer in. So the LDBC is short for Linked Data Benchmark Console, and now has developed three benchmarks: the LDBC Social Network Benchmark, the LDBC Graphalytics Benchmark, and the LDBC Semantic Publishing Benchmarks. And in this talk, we focus on the former two for the graph databases and for the graph processing systems, respectively. So overall, LDBC has a data model of social network with 14 entities, including the persons, and the 20 relation, including the nodes relationship. And it has a synthetic data generator with skill factors. And the workload are 14 complex queries, 7 short operation, 6 update operation. And it also has the business workloads with 25 complex queries. And it has the choke point designs with 8 categories. So for the data generation, LDBC introduced the correlated data generation, including 3 aspects. So the first one is attributes value correlation. So for example, the born place and the gender will influence the first name distribution. And for example, the Germany names are more likely to be associated with the Germany location, and the Chinese name will associate with the Chinese location. And the second aspect is time correlation. So this means people can post a comment only after becoming a friend with someone. And there are also trending events. So whenever an important real world event occurs, the amount of people and messages we're talking about this topic. So they will model these two scenarios in the time correlation. And the third one is the structure correlations. So this means the similar people will have a higher probability to be connected. So they will consider 2 factors in the structure correlation. For example, in order to generate the friendship, you need to use the multi-dimensional sliding window to sort the related persons based on the places where the person studied and the interests of all persons. And then they will pick the friends for a person to generate. So for the scaling data generation, LDBC uses skill factor valued from 1 to 1000. And the scale was determined by the setting the amount of person in the network. And for the largest skill factor, 1000, the generator now can be conducted within 2 hours. And the data generator is implemented on top of Hadoop, including 3 phases. First, the person generation, friendship generation, and the activity generation. So the LDBC also has a choke point design, and these choke point design are also inspired by the TBCH. So the original TBCH, as we mentioned before, has 6 categories: the aggregation performance, join performance, data access locality, expression calculation, correlated subquery, parallelism, and concurrency. And they also introduced 2 new categories: the RDF and the graph specifics, and the language features. So the RDF and the graph specific will consider some more graph-based feature. For example, one of the choke point will measure the query optimizer for the cardinality of transitive paths. And the language feature mainly focus on 2 graph query language, Cipher and SparkQL. For example, they will measure if they can express complex patterns, aggregation, and handling paths. So take the query 9 as the example. So query 10, sorry. So this query will focus on the friend recommendation, and it asks for a given person and to find this person's friends, and this person should be born on or after the 21st of a given month. And the final goal is to calculate the similarity between each person and the friends. So the common interest is defined as follows. The common means the number of posts created by the person, such as the post has a tag that the star person is interested in, and the uncommon is inverse to the common. So finally, the common interests equals to the number of common interests minus the number of uncommon interests. So this query actually involves 9 choke points, including the join type selection, common sub-expression animation, and the flattened subqueries. For example, this query will look for path of length 2, starting from a person to their friends and friends. So it does widely scattered graph traversal, and the join order here is simple, but one can see the anti-join or not in my friends is better with a hash. Also, they have the common sub expression for animation, and also these subqueries can be flattened. So the LDBC also formulates a problem of parameter curation. So the motivation that the benchmark specification provides the templates of the query with parameters such as the start person and the given date. So a conventional way to pick the parameters is to generate a uniform random samples. However, selecting uniform random samples from the domain only works if the underlying values are uniform distributed. And the uniform sample of person ID for this query will lead to the non-uniform distribution of the query runtime as shown in figure 5b, since the distribution of the two hop frame size is skewed. So as a result, the LDBC parameter curation is modeled as follows. So given an intended plan for the query, they will compute a parameter count table for the intermediate results in the plan. So the problem is to select a subset of size k in the PC table, such as the variance across all the columns is minimized. So they show that this problem is inverse to the NP-hard join ordering problem. As a result, they propose a greedy-based method in 2 steps. So the first step is pre-processing, which is to compute all the intermediate results in the query plan and store the information as a parameter count table, short for PC table. And the second step is greedily finding similar rows in the PC table, which is to identify the windows of rows in the column recursively. So for example, in this query 5 PC table, they will find the first column with the same count of 60, and then in the second window, they find the row with smaller variance. So finally they will pick the first 3 bindings of the person ID. And the second benchmark is LDBC Graphalytics for the graph processing platforms. So this benchmark includes 6 real datasets and 2 synthetic generators with t-shirt size. For example, XS, S, M, L, and XL. And more importantly, they has 6 implementations, including 3 community-driven systems, Giraffe, GraphX, and Power Graph, and the 3 industry-driven systems. For example, the PGX, GraphMat, and OpenG. So the workloads focus on the graph algorithm, including 6 graph algorithms: the breadth first search, the page rank, and the weakly connected components WCC, and the community detection using label propagation, and the local clustering coefficient LCC, and finally the single source shortest path SSSP. And the LDBC Graphalytics has defined a number of matrices, including 4 types. So the first is the baseline matrix, including the upload time, make span, and the process time, tproc. So the upload time defines the time required to pre-process and convert the graph into a suitable format for a platform. And the make span measures the time required to execute an algorithm from the start of the job until the termination. And finally, the pre-processing tproc measures the time required to execute an actual algorithm. And from the user level, there are 2 matrices: the edges per second EPS and the edges and vertices per second EVPS. And this matrix is computed by the number of edge divided by the tproc, or the number of edges and vertices divided by the t-prog. And the third one is scalability. Speed up is this is a ratio between t-prog for scaled and the baseline resources. So this means the ratio where measure how well a platform, when scaling the amount of available resources and the size of input, or both. And they also measure the robustness, including the stress test limit and the performance variability. So there are other graph benchmarks, including the link bench and BG for social network, and the graph 500 for graph analytics, and LUBM, BSBM, and the SP2 bench for the RD benchmark, and the GMark, which is a schema-driven graph benchmark, and the user can define the schema, input distribution, and query features for data and query generation. Okay, so next I will introduce the multimodal database benchmarking. Particularly, I will focus on our benchmarking system Unibench, which is a multimodal database benchmark. So conventionally, we adopt the polystore technique that employs multiple databases to satisfy the up-layer applications. So it follows the concept of one size does fit all. Unlike polystore, multimodal databases adopt the concept of one size fits a bunch. For example, a multimodal database can support relational, document, and graph simultaneously. So obviously, with multimodal databases, we can, to a great extent, reduce the integration, maintenance, and operational issues. So 3 representative native multimodal databases are OrangeDB, AgentsGraph, and ArangoDB. So for OrangeDB is a native multimodal database with a primary model as graph, in which every record has direct pointers to its neighbors. And these records can be documents, vertices, or even edges. And the AgentsGraph is another multimodal database that is built on top of a relational database, PostgreSQL. So AgentsGraph implements the graph model where the graphs are represented in index-based vertex and edge tables. And ArangoDB is a native multimodal database that built around a key value store in which documents are organized into collections. So furthermore, the graph model is implemented by the vertices and edge collections. So multimodal database have many applications. A typical one is the social commerce scenario that combines the social network and e-commerce. Suppose we have a nose graph in a social network and a customer table with orders information. So traditionally, we have to use a graph database like Neo4j to store the graph, and use a relational database to store customer tables, and use a document database like MongoDB to store the documents, and then write some customer codes to access this data. But now, multimodal database can manage these data and query them using multimodal queries. So for example, suppose we would like to make a product recommendation to recommend the bought cell phones by James to their two hope friends whose credit limit is greater than 3,000. By using a declarative query language, AQL in MongoDB, we can compose a corresponding multimodal query in a single statement. Particularly, we access 3 types of data simultaneously and specify or go to more details in the later slides. And table 1 gives a comparison of multimodal databases. There are 3 native databases, for example, the Agents Graph, MongoDB, OrangeDB, which supports the cross-model query processing. And there are original NoSQL database that extend their original data store to support the multimodal data management. For example, the Redis is the original key value database, and now it adds the graph and the JSON module on its key value store. And there are also cloud-based database like DynamoDB, which utilize multiple engines with corresponding APIs to support the multimodal like JSON, graph, and the key value. Numerous multimodal databases have been developed to facilitate the multimodal data management, but they differ fundamentally in data storage, query language, and query processing. So obviously there's a need for an end-to-end benchmark for multimodal database. However, there are several challenges for benchmarking multimodal database. First of all, so what is a typical application for multimodal cases? And existing application cannot be directly utilized to model our scenarios. And the second one is how to generate the data to simulate the real cases. And the third one is how to design the query concern technique and the business dimensions due to the huge space of the workloads design. And lastly, how to configure the query to consider multimodal characteristics. So to address these challenges, we develop a benchmark named UniBench for multimodal database. And it's based on a social commerce scenario with 5 data models: relational, JSON, XML, graph, and the key value. And it has a workload of 10 multimodal queries and 2 multimodal transactions with choke point designs. And we also define the execution rule that the implementation of query and data store can be different, but the input and query results for each test must be the same. For example, the input can be multimodals like JSON, relational, and a graph, and the query results must be a table. And the Unibench consists of three key components: data generation, workload generation, and parameter curation. So specifically, our generation is based on the three-phase framework to simulating the customer's behavior in social commerce. We collect the metadata from LDBC, Amazon review, and the DBpedia data. And we generate multimodal data based on Spark SQL. And the workload specification contains workloads, including 10 multimodal query and 2 transactions. And particularly, the design principle consider both the technique and the business dimension. For the business dimension, we design 4 business layers to cover various cases. And from the technique perspective, the queries are designed according to the 3 choke points. And the parameter curation is used to configure the binding parameter for the query. The cornerstone of this component is the NG-FAST algorithm, which characterizes the multimodal query by identifying the parameter as size vector. Then we use LHA sampling to choose the parameters. And our schema includes 5 data models. In particular, the relational model includes the structured customer and the vendors, and the JSON models contains the semi-structured orders and the products. And the social network is model includes 3 entities: persons, tag, and post with 3 relations. And there also have correlation across the data models. For instance, so the relational customer knows the friends in a graph, and the customer can make JSON orders. And our generation is based on a 3-phase framework. So in the purchase phase, we consider 2 factors. Persons usually buy friends based on their interests, and secondly, persons with more interests are more likely to buy products than others. And the person's interests for the product are generated based on power law distribution. And in the pro-purchase phase, we incorporate two factors. First of all, the person's basic data like gender, age, and the location. And the second is the average feedback from their friends. So we derive a scoring function based on the naive Bayesian method and the average rating of their friends. And finally, in the repurchase phase, we propose a new probabilistic model called CLVSC to make a fine-grained prediction by considering 3 factors: the expected number of the purchase behaviors, the expected monetary value, and the expected positive social engagement of customers. Okay. We collect the metadata from Amazon review And the LDBC graph and the DBpedia, we correlate the metadata using the realistic distributions. Specifically, we correlate the person entity in the LDBC with the country table in the DBpedia on the country field, and then we correlate the DBpedia with the Amazon review on the brand field. So moreover, we leverage the real data distribution to rank the values. That is the TPPD ranking for the country, and the Wikidata ranking from the brand, and finally the sales ranking for the products. With such correlations, so we generate the CDF distribution using the zip distribution, and then randomly generate the multimodal data. And the values are realistic. For example, China will correlate the Chinese name, and the USA will correlate the American name, brand, and products. And table 2 presents the results of the data generation. We leverage the data generator to produce 3 data sets with roughly size 1 gigabytes, 10 gigabytes, and 30 gigabytes by using the scale factor 1, 10, and 30. And in terms of the scalability, we successfully generate 30 gigabytes multimodal data on our 3-node multimodal our 3-node cluster. And the data generation is deterministic, meaning that the size of generated data sets with the specific scale factor is always the same. In addition, as shown in the figure 7, the percentage of the data size of each model has a stable distribution concerning different scale factors. We also have the choke point design in our workload. We consider 3 choke points from the technical perspective. The first one is choosing the right join type and order. The second one is perform complex aggregation. The third one is ensuring the consistency and efficiency. And all these choke points design involve the multimodal feature. So as for the join ordering, it requires the query optimization to find optimal join order for the given multimodal customer and product brand. The goal is to return these customers' friends within 3 hope friendship who have bought the products in a given brand, and these products have the 5 score reviews by the friends. So the execution plan are shown here. So we can see that the logic plan contains 3 types of join. The first is the 3 hope graph join, and the second one is the graph JSON join, and the third one is the JSON table join. So this requires the query optimizer to to estimate the selectivity of cross-model join and judiciously determine the optimal join order. So the second choke point design is aggregation. It demands a processing engine to handle the complex aggregation of multimodal data. For example, here for the query 8 performs the query 8 asks for all the products of given brand during a given year. The goal is to compute its total sales amount and measure its popularity in the social media. So this query performs first performs aggregation over the tabular data, and then it conducts embedded aggregation on the JSON orders. Finally, conduct aggregation on the popularity of the related tags. So this is a typical multimodal aggregation. The third choke point design is multimodal transaction. It tests the ability of the execution engine to handle the rewrite multimodal transaction while ensuring the consistency and the efficiency. So for instance, the new order will first create and insert the order, update the quantity of involved products, and finally insert the invoice. And for the payment transaction, first retrieve the unpaid orders and update the balance of the seller and buyer, and update the JSON order status to paid, and finally update the related invoice. So both transactions involve read and write operation on JSON files, tables, and XML data. So overall, the workloads of Unibench to 4 business categories, and including 10 queries and 2 transactions. So the first category is the individual, and the second category is the conversation, and then the community level includes 4 queries, and finally the commerce level for the complex aggregation. And all the queries involved at least 2 models along with different operators. For example, the query 2 will join data from a relational table, graph, and JSON files. And the query 5 will join data from relational graphs and the key value with recursive graph traversal, embedded document filtering, and relational joins. So moreover, in these 4 levels, we consider a lot of business cases, such as the customer 360 view in Q1, and the product recommendation in Q2, Q4, Q5, Q6, and the sentiment analysis in Q3 and Q7, performance transparency in Q8 and Q9, and the return analysis in Q10. So next, I will introduce the parameter curation. In our benchmarking process, we have a key observation that the same queries with different parameters differ in size of intermediate results. So for example, with 2 groups of parameter, pair A and pair B, the performance of ArangoDB and OrangeDB are completely opposite. For example, the ArangoDB is faster than the OrangeDB with pair A, and OrangeDB is faster than AngularDB with pair B. So we found this is because the query with pair A will involves relative larger intermediate results of JSON, while query with pair B takes it in the larger size of graph. So this will result in the, different benchmarking results. So the question arises is that can we devise an efficient and transparent method to control the query parameters? However, there are several challenges for this problem. The first one is how do we represent the size of intermediate results from the data model perspective? Because in a multimodal query, the intermediate results can vary. And the second one is how to select the parameters efficiently and comprehensively. And the third one is how to cover the various workloads concerning the data model to introduce the query diversity to the benchmarking process. So to address these challenges, we formalize a new problem called multimodal parameter curation that is aimed at diversifying the query selectivity under the control of parameter curation. So first of all, we define the diversity of the size vector as the normalized Euclidean distance. And then we define the problem of multimodal parameter curation. Formally, so giving a multimodal query queue with a d-dimensional parameter domain that is a Cartesian product of the base domain as well as the size k. So the objective is select a subset of the parameter domain such that the query diversity of the subset is maximum. So for example, for the query for which is to find the person's friends who have bought products with brand B, so concerning the query for a person P and a product brand B, to find the P friends who have bought products with brand B. So for this query, the parameter domain include the domain of person ID and the domain of brand, and these are the parameter value of in the domain. So first of all, we represent the size vector involves the multimodal intermediate results. So for example, this query will involve two base dimension graph and the JSON short for G and J, and also their join results, which is represented as GJ. So by computing these values, so our goal is to we would like to choose the rows in blue colors, which has a maximum diversity of 1.5. So we employ the Latin hypercube sampling, short for LHS sampling. So LHS sampling is a multi-dimensional stratified sampling method that can improve the coverage of the input space by independently sampling values from non-overlapping segments. So our main idea is that, well, it is hard to compute all the size vectors, the intermediate result size of the base dimensions, such as the base dimension of graph and JSON, and they are independent and can be individually computed beforehand. We then employ the LHS method with to guarantee the size range of the base dimension are fully represented. So for example, for a two-dimensional space, we bucket their values into 4 size ranges, and we also bucket the size range of JSON to 4 buckets, and then we can sample the value with non-overlapping segment to feed to our parameters. So in summary, we propose a MJ-fast algorithm with 3 steps. First of all, it identifies the base dimension for each data model and computes the intermediate result size regarding each base dimension. And then we employ the LHS method to select the size vector, so which divides the size range of each base dimension to k segments. And then we sample the k size vector from the k-dimensional buckets. And finally, we map the size vector to the corresponding parameter group for configuring the queries. So this will make our benchmarking process more fair and more robust. So we have compared our MG-fast algorithm with the random sampling method. So first of all, we generate the parameter faster than the random sampling. So the reason is that our method only computes the result size for base dimensions, where the random sampling will compute the whole space of the size vector. And the second picture shows that the parameter curated by our approach have a much higher, approximately 3 times larger diversity compared to the random sampling. And the third picture shows that our method yields 2 times smaller KL divergence than the random sampling, indicating that our approach is much robust than the random one when generating the parameter multiple times. So for the DB layer implementations, now Unibench has implemented all the design queries in Orange SQL, SQL Cipher, and AQL for the OrangeDB address graph and the ArencoDB respectively. So we use again an example of Q5 to illustrate the implementation of the query language. So the Q5 is to find the 3 host friends of a given friend with the bot orders in brand Nike, and then the feedback should have the 5 rating. So the ArencoDB used AQL following a for in filter return syntax to access the data in specific. So the line 1 to 3 operates on the graph JSON and the key value data, and the filter condition contains the cross-model join predicate and the filtering predicate. So in line 5, it uses a widecast operator to access the brand element in the array. And the OrangeDB uses a SQL-like query language. So note that the join syntax is not supported, where it uses a chain or path-oriented dot operation to link the data. So like the order.items.brand and feedback.rating. And it provides a traverse keyword to traverse the graph. And it adopts a select from where SQL syntax, but the sub-SQL query is embedded in the from clause, not the where clause. So furthermore, to access the embedded JSON document, it has to flatten the nested documents to multiple single row documents, like on line 7, the on-when will flatten all the items array. And finally, the agents graph uses the SQL cipher syntax. So interestingly, this query is represented by two multimodal inner joins. The first inner join is between the relational table and the items in the array. And then the second join is between the intermediate results with the graph data. So particularly line 3, we use the JSONB array elements to retrieve the item arrays in the JSON orders. And in lines 7, 8, it leverages the cipher syntax to traverse a nose graph. And we also implement this query in sparse SQL, because nowadays the sparse SQL can handle various kinds of data, such as graph, key value, and JSON data. And particularly sparse SQL uses data frame as the data abstraction specifically. So for this query, the line 1 to 6, it loads the CSV, JSON, and the graph data from the HDFS. And in line 7, it uses a graph frame to load the graph. And in line 8, it uses a multi-finding operation to find the two hope friends. And in line 9 to 11, it returns a person with distinct person among the friends. And in line 12, it finds the JSON order with the Nike brand. And finally, the performance inner join between the orders and the friends. Experiment from our evaluation. So for the data importing, we compared agents graph, ArangoDB, and OrangeDB, and we found that from all the data sets, agents graph, which is based on a relational store, is roughly 1.5 and 9 times faster than the ArangoDB and the OrangeDB. And we found that because the agents graph use the tables to store all kinds of data, so the transformation cost is the lower risk. And the second experiment is about the query performance. So for query performance, we found that the OrangeDB is excel at the graph-based query, like query 3 to query 5. And the ArangoDB is best at document filtering with join queries. And the agents graph outperforms the others in performing the complex aggregation queries from query 7 to query 10. So the main observation is that the query performance actually is highly relevant to their main model. So for example, the OrangeDB is based on the graph model, and ArangoDB is based on the JSON model, and the agents graph is built around a relational database. So for the transaction performance, we found that the OrangeDB is more efficient in performing the read-heavy transaction because the data is linked in OrangeDB, and the agents graph and ArangoDB are better at write-heavy transaction. And overall, the agents graph is roughly 3.4 times and 10 times faster than ArangoDB and OrangeDB. So this is mainly because the relational engine, which has advanced and matured concurrency control in agents graph. So we also compare the query performance in distributed execution with the SparseQL. So we found that the SparseQL is roughly 10 times faster than ArangoDB and 50 times faster than OrangeDB in data importing, because in SparseQL, they simply copy the local files to the HDFS store without any transformation. And for the selection and the join task, the OrangeDB is a winner, which is roughly 13 faster than ArangoDB and 2 orders of magnitude faster than SparseQL. So the SparseQL is slow due to the absence of index, and for the join task, because the SparseQL has to do the shuffle phase, so it's costly, and where the OrangeDB has the local index, which can accelerate the query significantly. And for the aggregation task, SparseQL is 1.6 faster than OrangeDB by using the multiple RDD partitions. So in the next, we will demonstrate how to use the Unibench to benchmark multimodal database, ArangoDB. Hello. Now we demonstrate how to run Unibench for ArrangoDB. So first of all, we clone the Unibench and change the working directory to Unibench2. And we change the parameter of the LDBC and Unibench to configure the skew factor. So we configure the LDBC skew factor 1 and use the default serializers. And similarly, we use the skew factor 1 to the multimodal data generation. And then we restore the dependency and combine the Unibench. We combine the LDBC as a Maven project, and we combine the Unibench as SBT project. And the data generation consists of 2 steps. The first step is to generate a social network. The second step is generate a multimodal dataset. Okay. So the LDBC is implemented on MapReduce. So it will use multiple MapReduce phases to generate the data. This phase took total execution time 134 seconds. And under the LDBC directory, we can see the social network graph has been generated. Okay, so the next steps is to generate the multimodal dataset. So the Unibench data generator is implemented on SQL, on Spark SQL. So this process will assign multiple executors to generate the data. This process took total time 160 seconds. And you can find the data under the Unibench, including the CSV products, the invoice, the order, the feedback rating, and the windows. And the next step is to benchmark the ArrangoDB with Unibench. First of all, we import the generated data set to ArrangoDB. We use our data importing script for ArrangoDB. And we use the 8 thread to import the data in parallel. So the importing process took 2 minutes and 15 seconds. And all the data has been imported. So by looking at the AringoDB web interface, we can see the AringoDB uses two types of collection to store the data. The vertices collection and the age collection. So for the document collection, so each document will be treated as a row, and each row is represented as a document with the ID, the revision key, and the primary key. And each age collection represents an age from a vertex to another vertex, and the age can have the attribute. The next steps is use Unibench to do a power test, meaning that we will run the queries in a sequence. And the running time for each query will be reported. We can also do an in-depth analysis in the AringoDB web interface. We take a query 5 as an example. So this query first find the friends of a given customer and their bought orders in brand of Derby. And finally, we'll find the related tags for these friends. And so this query takes roughly 9 seconds, and the results will be returned as tables and or JSON format. By explaining the queries, we can see what indices and what's the graph traversal and what's the optimization rules have been applied. And for the execution plan, the query optimizer may make an estimate for each node in the execution plan. So here we can see for the cross-model join between the order and the graph. So due to there are no indices available, so the estimation cost is much higher than other nodes. Thank you. Thanks for your watching. So recently, we are working on Unibench version 2 to incorporate more data models. For example, we have enriched our data model with RDF data, and we are now adding more cross-model queries accordingly. So please stay tuned on our GitHub project. There are other related benchmarks involving data variety, such as TBCDI and Polybench. First of all, the TBCDI target at the data integration systems, and it has multiple data models, which simulates a retail brokerage firm's information systems, where 5 different data sources have to be integrated to a decision support system. So its focus is on the ETL process, and the workload consists of 17 transformations from source table to target table. For example, they will transfer the JSON, XML, or text to the tables, and it defines 4 phases of the execution rules. So the first phase is the initialization phase, which is untimed phase, and then the historical load phase, and the incremental update phase, and the incremental update second phase, and finally the automated audit phase. So this execution model consists of both timed and untimed parts, and it's not permitted to begin processing of a phase until the previous phase has completed. So the second real work is the polybench. So polybench is a benchmark targeting at polystone systems. It also has multiple data models to simulate a banking business scenario with 8 models. And for the workload, the authors designed 3 user cases for banking data analysis. And for the execution rules, it considers the one-shot scenario and the continuous scenarios. Okay, and finally, we discuss some open challenge and future directions on big data benchmarking. So there are a lot of open challenges on big data benchmarking. It has been pointed out that big data benchmarking have a number of pitfalls. So number one is non-reproducibility. So meaning that now the benchmarking tools and the benchmarking results are a lot of reproducible, because the benchmarks are not open source, either open source or the results are invalid. And number two, failure to optimize. So this means a minor tuning can change the result significantly. So for example, in our problem or parameter curation, so different parameter values will result the opposite performance results. And number three, apples versus oranges. So this means a comparison is not fair, and we compare totally different system to get the results. So for example, if we use the in-memory system use a in-memory system to compare with disk-based systems, so the results are meaningless and not convincing. And the number four is the incorrect results. That means the benchmarking results are not valid. And the number five, cold versus hot run. Number six, data pre-processing, which has led to the unfair results. And final one is overly tuning. So from my point of view, I gave in this tutorial 5 future direction. So the first one is verifiable big data benchmarking, meaning that we can make the benchmarking toolings open source and reproducible, of course, and we can also do fine grade benchmarking to verify our benchmarking results. So a good example is SQL scalpel, so which enumerate the subspace of the predicates to identify the points that lead to the performance regression. And the second direction is the probabilistic big data benchmarking. So for this case, we can treat each test as a trial. And so in this case, we can give a system A is greater than system B with some confidence interval without determinist results. So for example, giving 7 paired observation with the let's say latency results between A and B. So in this case, we can do a t-test to get a 99% confidence interval between the -1.21 and the 3.27. So in this case, instead of using the mean latency, we can say we give a confidence interval. So in this case, actually the A is same as B statistically, because the 0 is a part of the confidence interval. So we cannot say A is greater than B, but statistically A is same as B. And the next direction is I'm thinking is the personalized big data benchmarking, because nowadays from a user point of view, the user can define their own requirements and their own matrix, or user can define the component that they want to benchmarking. So, and in addition, user can do interactive benchmarking for a personalized benchmarking tooling. And in the benchmarking process, user can debug the whole process and stop some process immediately, or pause some process and then continue. And the fourth direction is automatic big data benchmarking. So this means that the benchmark tuning can be automated without the human effort, because now the benchmarking tuning is still heavily rely on humans' effort. So we need smart benchmarking tool. So from 3 aspects. First is automatic data accretion and workload generation. The second is automatic experimental setting up, and finally we can get automatic reports with insights. And the last but not least is about benchmarking results reuse. So because nowadays we have a lot of useful evaluation results, and we can collect the valid insight to save time. That particularly we can we may build the knowledge graph for future use. So also we can trace the system evolution, etc. Okay, thank you for your attention. Now we are happy to take any questions. Thank you.